Alright, so here we are with Unit 9, Lesson number 6, and this is the alternate theory that we were talking about before. It's not asked about a heck of a lot on the Regents exam, but on occasion they do show you it, and again, they're going to refer to it as the alternate acid-base theory. I haven't seen it referred to as the Bronsted-Lowry theory. It's just another way of identifying acids and bases, because not all acids and bases behave like Arrhenius acids and bases. In other words, not all acids begin with the letter H, or the element hydrogen, and not all bases necessarily have to contain OH. You can have Bronsted-Lowry acids and bases, and here's how you identify them. And it is a little tricky, so let's go through this quickly. And again, I'm not going to spend a lot of time on it because, well, it's not asked about a lot, but I just want to go through it. And I don't think these diagrams are very good, so I'm just going to write. So here we have HCl, and we're going to react it with water. Now, in the normal sense, we would say that's an Arrhenius acid because it begins with H, and we'd say, well, water is neither an acid or a base. But watch what happens here. If you look at these other reactants and look at what forms here, as we had talked about before, you're forming a hydronium ion and Cl minus. So forgetting about what you learned with Arrhenius acids and bases, let's look at it a different way. Remember, these are the starting substances. This is what you had before, and this is the after. So if you look at here, you notice that this is HCl, but look at what happened to it on the, sorry, look at what happened to it on the other side. Let me go back here again. Here's HCl, and you're reacting it with water. And here's what forms, H3O with a plus, a hydronium ion, and a Cl minus. Let's kind of take a look at it from as a before and after. You notice that you have HCl here, but look at on the other side what has happened. Obviously, this H left was pulled off of this chlorine. Well, where did it go? This H joined up with the H2O, and it formed H3O plus. The chlorine was left basically by itself. So the way that you would identify this is you would say that the HCl donated an H plus ion. It lost an H plus ion, which they sometimes refer to as just a proton. So if you are a proton donor, an H plus donor, you are considered to be a Bronsted-Lowry acid, a very different definition than Arrhenius acid. In a Bronsted-Lowry acid, when you're in a reaction, if you lose an H plus, that means you're a proton donor, you're an acid. Now the H2O in this particular case accepted the H from the HCl. So a proton acceptor or an H plus acceptor, in other words a compound that takes an H plus ion, is considered to be a base. So a Bronsted-Lowry acid is a proton donor or an H plus donor, loses an H plus. A Bronsted-Lowry base accepts a proton or a H plus ion. And so one of the things that you have to be able to do is if you're given an equation like this one right here, let's go through it and show you how to do it again. So here we have H2O, and that's reacting, that's NH3. So if you look at it, you notice that this is H2O, which you can write as HOH, right? What's going to happen here is that this H is going to be donated to that, and it becomes OH minus. If the NH3 gains an H, it becomes NH4 plus. That's NH4 with a plus. So this donated hydrogen, that makes it a Bronsted-Lowry acid. This accepted it, makes it a Bronsted-Lowry base. Okay? And again, apologize for that. Now, one of the things that you have to be able to do, and they don't always do this, but we're going to have to go through it anyway, is if you're given an equation, you have to be able to do something called the Bronsted-Lowry conjugate acid-base pairs. You know, if you remember back in Unit 8, I believe, as you see this double arrow, that means it's reversible, which means you have to read it in two directions, from left to right and from right to left. So there's actually two reactions going on simultaneously. If you read it from left to right, you have to be able to determine which is the Bronsted-Lowry acid and which is the base. The HCl loses the H to the water, so it is a Bronsted-Lowry acid. It becomes, on this side, just Cl with a -1. the H2O took that H from the Cl and accepted it, makes it a base. So that's the base. If you're going in the other direction, this is where it gets tricky, right? Completely from the opposite direction. Now these are reversible reactions. So now the Cl is going to collide with the H3O. It's going to take the H back that it originally had and become HCl. So this is going to be, if it accepts a proton, this is going to be the base on this side for the reverse reaction, and that would be the acid. So one of the things you have to be able to do is you have to pick the acid on one side and its conjugate base on the other. So the HCl is an acid on this side, but in the reverse reaction it acts as a base. So that's one conjugate acid-base pair. This is the other conjugate acid-base pairs. And again, I'm not going to spend a lot of time on it because I don't want to have this video too long. And that is a couple of examples. I'm not going to spend time going through this. We will go through this in class, so remind me to go through, Mrs. Lindsay, the practice problems that were on the video. You should try them out, and if you're having problems with them, then let me know in class. And that is it for this lesson. I'm going to go through one more thing here. This term, amphoteric or amphiprotic, it's not asked about on the Regents exam, so we are not going to, just for a little bit of, save a little bit of time, we're not going to worry about amphoteric or amphiprotic substances. And that is it for this particular lesson.